Okay, so the problem is to reorder the routes to make all paths lead to the city 0. We have n cities, let's write this here, n cities, and n minus 1 roads, n minus 1 roads, such that there is only one way to travel between two different cities. So if I have two cities, there is only one way, not two. This network forms a tree. Last year, the Ministry of Transport decided to orient the roads in one direction because they are too narrow. So not only there is only one route from one city to another, it also has a direction. Roads are represented by connections. Connection of I from AI to BI represents a road from city AI to BI. So we have a city A, and then we have a city B, and then we have a connection, and we do have connection between all the cities because we have n-1 roads and n cities, and there is only one row between each city, so all cities are connected. So this is the representation. A, I, B, I. And there will be a big event in city 0. So if this is city 0, there will be a big event here. And we need to make sure that all people from all other cities can reach eventually this city. So if we had, for example, a case where we have here city 0, and we have this direction and then this direction, then the people from this city cannot arrive to city 0 to the happening. So your task consists of reordering some roads, reordering some of the roads, such that each city can be, each city can visit the city 0. Each city can reach the city 0 and to return the minimum number of edges changed. So note that we need to return only a number. This is very important. Return only a number, because if we do the actual changes or return the actual changes, we don't need to return them. We only need to count. This may is the problem. It's guaranteed that each city can reach city 0 after the reorder. Okay, so let's draw again this and see how we can solve it. So we see here in example 1 that we had 4 can reach 0, all is okay. Here 5 cannot reach 0, 5 can reach 4 only after we change this. 1 cannot reach 0, we need to change. 3 cannot reach 0, 2 after these changes can reach. So we had 1, 2, 3 changes. Let's look at it again. We can start from 0 and then check the upcoming edges. Can you reach 0? So it's the neighbors. Check the neighbors of 0 and ask a question. Can you reach 0? If no, we mark a change. Plus plus change. Can you reach 0? All is okay. No need for a change. Now ask the friends, the neighbors of these next nodes and the neighbor of this. Again, can you reach 0? So see that we repeat the question. But each time we repeat the question, we ask it on a different node. In the first node, we ask the question on node 0, and here we ask 5, can you reach 4, not can you reach 0. So we repeat the question on different nodes. And we traverse this graph, each time on the neighbors. So we need to do traversal, ask question in repeat, ask question on friends, and repeat. And we need all the common terminology of nodes, edges, and we need also to count, to do some work, and we need not repeat the same edges, so we're going to have a visited array. Okay, so let's now go to the actual coding. Okay, so we are now going to actually implement it. We see that we have min reorder, the number of nodes, and then all the connection. This is an ordered list of connections. So if we look at the examples here, we see that we have 5 nodes here. It says 5, 1, 2, 3, 4, 5, right? Then we have an edge from 1 to 0, 1 to 0, and then we have an edge from 1 to 2. Yes, 1 to 2, not from 2 to 1. If there was from 2 to 1, we should have seen here 2 to 1. Okay, so let's approach it with the method that we said. So in all these questions, we need to traverse something. So we need to start from 0. Start from 0. See if all the nodes point to it. If not, change and increment. Okay, start from node 0. We need to have a counter. Let's say changes plus plus that will increment every time we think we want to make a change, because they didn't ask to return the actual changes. So when do we make this change plus plus? We check if adjacent nodes can reach this node. In first case 0, in other cases the other nodes. So we have our loop, we have our recursion, start from the first node, see how many changes plus plus we need to do for each neighbor, move to the next node recursively. How do we move to the next node in graph? We can do this in multiple ways. Move to next node, we can do BFS, DFS, doesn't matter here. And note that in BFS DFS, when we examine the neighbors, we always ask, is this neighbor already visited? Because if it is already visited, then do no action. Is visited node? If yes, do nothing. Else do action, which is to check the differences if we need to upgrade the changes. Okay. The way we are presented with the nodes is not that convenient, because if I need to know if there is an edge from 3 to 2, I need to scan this array, and only here I see it. It would be great if I could have all the edges immediately accessed all of one to understand if so when I'm here at 3, I want to know if it points to 2. So I want to get this edge to see if it exists. If not, then reverse. Another thing, I want to start from node 0. Then I want to find all the nodes that are adjacent to it, all the neighbors. So I need a map from a node to its adjacent neighbors. I need a map from a node to its neighbor. So I'm going to create these two auxiliary data structures. Let's start with the neighbors. From a node, map of from a node, each node is a number, into a list of neighbors, because there can be more than one neighbor. Neighbors, new hash map. Now each edge is a pair, so there is no in Java 8 any pair except for JavaFX and stuff like this, so I just copy pasted here a pair. This can be done otherwise, but it's much cleaner like this. So set of pair, this would be the edges. Edges, new hash set. And now we would also want to count the changes. Int changes is starting from 0. And we also want to see which nodes have already been visited, which is this new hash set. Okay, so we have our basic data structures, and let's start coding. Ooh. Okay, so graphs. We have neighbors, we have edges, we have something to do on the graph, and we have the visited. This is almost common to all graph questions. Now let's build this data structure. So for int, we are now building both the edges and the neighbors. For each connection that we have in the connections, for each connection in the connection is between two nodes. As we see here, it's a small array of 2 items. So it's a small item of 2 items. For each connection in between the edges, if both, let's edit, but in order to edit we need to edit, because there could be multiple target nodes, so we need a list, as we said. So if neighbors dot get, if I didn't yet edit at this node, then edit with a neighbors dot put fs, and we put here the array list so that we can add all the edges. Same for the other edge, actually. Same for the other node on the connection. If the node connection is null, okay. Now let's add the neighbors. Neighbors dot get con 0. Okay, and we add the first neighbor, the first node to the neighbor, the first neighbor to the node. We are now scanning all the items and building the neighbors data structure. Neighbors get con 1 add. Now let's say that the other one, this is undirected. I just want to know what are all the neighbors and then to check the edge. Okay, undirected, just check all the neighbors. And now let's create a function. We'll scan now all the items with the function, and We start from node 0. So we're going to do what we just said. Is there an edge from all the neighbors to this node? If there is any neighbor which does not have an edge to this node, then it's time to edit. Okay. Then, so let's scan all the neighbors. Let's scan all the neighbors. Okay, is this neighbor already visited? If this neighbor already visited, nothing to do. If this neighbor does not have an edge, from this neighbor to our source node, from the neighbor to the source node, we do not have an edge, then we increase the changes. Okay, we visited the node. We visited the neighbor. We continue to this neighbor, visit it, and continue scanning its other nodes. And now we need to return the changes, return changes. And now we had here a bunch of variables which the internal function is not aware of. So this is a programming interview, just move it to the top of the class. Okay, so let's now look at this. So we have all the neighbors, a map from each node to all its list of neighbors. We have all the edges much more conveniently to get. Give me this edge. Does it exist in the set? In order to know if the neighbor has an edge to the source node. We're traversing graph, so remember all the nodes that we've traversed in order not to traverse them again. Initialize the neighbors again, from each node to all its neighbors. This is neighbors. We didn't initialize the edges. Okay, so initialize the edges. So for each such connection, we create a new pair so that we can compare it with each edge. So we can do immediately, edges is a set, so we can check immediately the set if we have such an edge. So we initialize the edges. This is directed. These are all the edges. And then with dfs, go over all the neighbors of the city, input city, check. It's a graph. Check. If we already visited it, the basic thing in graph is to visit nodes. Then check if there is an edge from the target node into the city. If no, then increase the changes. In any way, add this edge. Add this edge to the visited, so we don't visit it again because we already visited it. Already visited means already did the work, because we are now like visiting it with the TFS. So visited is a little bit misleading. We are now visiting it. Work done. You can call it work down nodes. And I have here a small implementation of pair for Java. Let's run the code. Compile error. Neighbors, line 3, Let's see, 93, 93, 93. Yeah, I think, yes, here it's missing. Okay. Band code. New hash sets, set of pair, new hash sets. Where is the issue? Set of pair, yeah. New hash set, let's run it quickly again and hope it's now passing. Thirty-two. DFS, public. Yeah, we didn't have here a closing brackets. $129. What's there is an addition? This looks additional one. Class pair should be static. I see. Yes, we should remove this from the end of the class and add this here. I don't do proper indentation because I'm on a tablet, so it's hard to do all the indentations now. Cannot find sample set of integer. Yeah. Okay, it's a little bit hot, please. I'm on a tablet. Line 36. Too many compilation errors in tablet. Don't work on tablets for programming. Line 36, let's see. Very challenging. 36 looks good. What's the problem? Contains. Oh my god. Line 87. Yeah, I'm missing here some fields. I wish there was in native Java a pair, at least in Java 8. Maybe in future Java there would be. And line 31, this looks closer to closure. 31, what's the issue, man? Don't see the issue. Oh, the return should be here. Tablet, no indentation. Okay, finished. What? Didn't I increase the... Didn't I initialize it? Edges dot add new pair. Yes, I did initialize. I did. Okay, I didn't call the function. We don't want to do double check. To double check the... Okay. Even with a few words I make this mistake. Visitor.add. Okay, so we go through each of the neighbor, check if it has an edge to the source node. If not, then recursively we go to the next one and submit it. And then we check for each node with DFS if it has, and looks good, looks like it worked. Okay, so this was it. Problem 1466, reorder routes to make all paths leads to city 0. Thank you for watching and see you guys next time.